Hi folks, welcome to lecture 2. In this lecture we're just going to have a brief introduction to linear functions, the first of the functions we're going to examine this semester, and then we'll have a quick look at solving linear equations. So just to give us a kind of bit of an overview of how the module will progress, we've looked at functions in the previous lecture. Now we're looking at linear functions, and then we'll move on through these other functions as the module progresses. So, linear functions, how do we recognize one? The main way to recognize a linear function is there's no power on the input. So here, remember guys, this is the input and this is our output. So there's no power, there's no squared or cubed or anything like that. So the highest power, just to be a bit more formal, the highest power on the input is 1. And that's how you'll often see a linear function being defined. Here's another linear function. Here's another one. Again, h is the input, h to the power of 1. So the main thing, guys, is that there's no powers on your input. Then you know you're dealing with a linear function. This one looks a bit more complicated. This is our convert Celsius, so that's the input, into Fahrenheit, which is our output. So the simplest equation is just y is equal to x. More generally in science, a linear function is given by y is equal to ax plus b. In the Leaving Cert, this was called y is equal to mx plus c, and I'm going to stay with this notation here. I've tried using this a few years, and generally students don't seem to like it that much. They prefer what they're familiar with. So that's why we're going to stay with this notation here. And we'll examine what m and c means in the next lecture. So when you draw a graph of a linear function, you always get a straight line. That's where the word linear comes from. So when anyone talks about linear, they're talking about a straight line development. There's a typical graph, ax plus b. For every input, a single output value exists. This produces a continuous line. So what we're talking about here is it a function as opposed to just equation? It is. And it's a one-to-one function. Slope never changes. That's essential. And for this reason, guys, this is why we like linear functions for analysis. And as the module develops, we'll see various ways of converting, say, an exponential curve into a straight line curve, and that allows much easier analysis. So linear functions are our favorite when it comes to analysis. Just a few examples. You need to know these guys. I will always be looking for, when we talk about linear functions, you need to know its simplest equation, its general equation, what a graph looks like, and a few examples of where linear functions occur in the real world or in science. So the circumference of a circle is an example of a linear function. There's only one input, which is r, and the highest power is 1. Perimeter of a square, similar. And any conversion factor is a linear relationship. Here's our Celsius into Fahrenheit function again. We'll be coming across this a lot in the start of this semester. We'll be working with this function again and again in various guises. Just with conversions, guys, you got to be careful. Usually a conversion is written with the input written first. 1 kilo. So what we're going to change is the input, and what we change it into is the output. Usually In functions, though, in normal kind of science functions, the input usually appears on the right. But again, it doesn't matter which side it appears on. Whatever is written on its own is the output, and then everything else is the input. So in the lowest function, the Celsius function, we're changing Celsius. We feed a Celsius value into this function, and a Fahrenheit value is outputted. So it's really important, guys, to get this idea of input and output sorted early on in the module, because we'll be referring to it again and again. In an experiment, you control the input and you measure the output. And that then is how your graph is drawn. The input always goes on the horizontal axis and the output goes on the vertical axis. So if we were to draw a function of that lowest function, Celsius would be here and Fahrenheit there. Proportional linear functions, we looked at proportionality at the end of lecture 1. In a proportional linear function, so just like with the circle, remember a proportional function is one circumference, is where there's only one term on the input side. So this is a proportional function, but the function we just looked at, this is not a proportional function because there's two terms on the input side. So if there's only one term on the input side, you've got a proportional function, and what that means, guys, is your straight line will pass through 0, 0. And again, proportional functions are the best to analyze. They're our favorites. So consider the circumference of a circle. C is equal to 2 pi r. So say if I let the radius be 6 centimeters, when I multiply 6 by 2 pi, this is now my circumference, and this is my radius. Now, if I double the radius, that doubles the length of the circumference. Now, I know this seems obvious, guys, and I'm laboring the point deliberately. The reason why I'm laboring it is linear functions are the only functions which have this property, that if you double the input, it doubles the output. A lot of people kind of go through the world thinking everything is a linear function. If I double the money I put into the bank, then I'm going to double the money I get out at the end. That's not going to happen that way, because banks and interest rates operate under a different function, usually an exponential function. So this doubling, if I double the input, doubles the output, that only applies to a linear function, and a proportional linear function in particular. So just some of the things we need to know. This is just a quick review. I put up one of these slides for every function, and this is kind of the essence of what you really need to know. What the graph looks like, what the general equation is, just a little bit about the function. And then I'm always looking, guys, that you have at least 3 examples of a linear function in the real world. So there's 3 there. So this slide here, guys, definitely remember all these bits. And on each of the 7 functions, guys, I have one of these slides, and I will always be examining it as well, just because this is the essence of what we're doing. Just a few examples. Those ones are very simple ones. So if your car travels 10 kilometers on a litre of petrol, well, then it's going to travel 20 kilometers on 2 litres of petrol, 30 kilometers on 3 litres of petrol, etc., etc. If you have no petrol, then your car will travel 0 distance. And again, we'll be passing through that 0, 0 line, that 0, 0 point. When you pay VAT, say 23% on goods and services, again, if you spend 100 quid on, say, goods, then you're going to pay 23 euros in VAT. If you spend 200 euros on goods, then you're going to spend 46 euros on VAT. So that's a linear function. Service charge in a restaurant is similar. Again, if you don't buy a meal in a restaurant, you're not going to pay any service charge. So most retail transactions, one apple costs 60 cents, two apples costs 120. These are all linear functions. They're everywhere. We're kind of so familiar with them that you don't actually recognize them. Then there's non-proportional but still linear functions. Taxi ride would be an example of this. Because if you jump into a taxi, technically once you jump in, you have to pay the taxi driver the pickup fare. And then you pay per mile. Waste collection, a lot of bin companies operate on a monthly charge. So even if you don't get your bins picked up for a month, you still have to pay the monthly charge. Landline, again, there's the service charge, and then you pay by call, etc. as well. So these are all linear functions as well, but they have this extra bit. And we'll discuss this in more detail in lecture 3. We'll look at a few practical examples of these types of functions. So now we're just going to introduce solving linear functions. Most of you are very familiar with this from school, but it's just to kind of lay down the ground rules. So first of all, what does it mean when I solve an equation? When x is equal to 6, what does that mean? So this is a typical linear function. Highest power on my input is x. Sorry, highest power is 1. My input is x. And this, guys, is not going to be a proportional relationship because there's two terms. I know just by looking at that curve, because there's two terms, it is not going to pass through 0, 0. And we can draw a graph of it, and here's the graph, and we can see again the line doesn't pass through 0, 0, it passes through here, hits the y-axis there. Now drawing a graph, guys, every time you need to solve a function is just not practical. And graphs, especially hand-drawn graphs, are just not very accurate. So when we solve an equation, the output becomes 0. So graphically, what we're looking for is where the line cuts the x-axis. Now I'll explain that in a minute. So from the function's point of view, we're really asking, well, what input, what x value will give me an output of 0? There's my line, y is equal to 0. That horizontal line represents y is equal to 0. And we're asking, well, what's the x value? Where does the curve cut that horizontal line? That's what we're really looking for. What input will give me an output of 0? So most of you are familiar with this, just to kind of, it's like our formula manipulation. We want to bring the 5 over, so we add 5 to both sides. Now we want to just get x on its own, so we divide both sides by 2. And now we know that the input that gives us an output of 0, that input is 2.5. And we can arrive at this, guys. We don't need the graph at all. Sorry, that's just bounced up early. So think of our Fahrenheit function. F is equal to 9 over 5c plus 32. So again, guys, this is a linear function because the highest power on my input is 1, but it's not proportional because there's two terms in it. If we solve this function, it's the exact same as before, guys. We're going to subtract 32 from both sides to move the 32. Now we want to get rid of 9 over 5. It's joined on by multiplication, so we divide both sides by 9 over 5. But if you remember from semester 1 and fractions, if we divide by a fraction, it's the same as multiplying by its reciprocal. Flip and multiply rather than dividing by the fraction. So that's what we do, guys. We multiply both sides by 5 over 9. When we multiply the 9 over 5, by 5 over 9, we end up with 1. So that's what we're doing there. So I just moved things around a little bit and tidied it up. And now we've solved for C. We just get our calculator, and this is our result. So 0 on the Fahrenheit scale is the same as minus 17.8 degrees Celsius. And this is just a graph. And again, so this is what we're looking for. Where does the line cut the x-axis? And it cuts it here. And again, guys, you can see even if we had spent ages drawing this graph, it would be quite hard to get from this graph to determine, oh, it's exactly minus 17.8 Celsius there. So using the analytical method is always more accurate than using a graphical method when solving functions, especially if your graph is hand-drawn. If it's drawn by a program or something like the graphing calculator I have, then we can get high levels of accuracy because they're using this in the background anyway. So how to solve? Just a little bit of a more formal approach. Get rid of any fractions if necessary. Use a common denominator or cross multiplication. Gather all the unknown terms to one side. Move everything else to the other side of the equal sign. Most of you are familiar with this, I think. And then solve for x, or the unknown. Here's just an example. Solve for x. I want to get x on its own, guys, so my first step is subtract 3 from both sides. We'll get 5x is equal to 20. And then we divide both sides by 4. And we get x. So divide both sides by 5. Please forgive me, not paying attention. And I get my answer then, x is equal to 4. So if I was to draw that graph, I now know quite a lot about it. I know it cuts here when x is 4. Another example. Now there's no fraction terms, so we're okay for the first bits. We need to gather all our x terms to one side. So I'm going to bring this x over to the left. I always figure out, well, where is x going to be positive, and I move everything to that side. I hope that makes sense. So I'm going to subtract x from both sides. We'll get 7x minus x on the left. And at the same time, guys, I'm going to move this 8 over to the other side, and I'm going to add 8 to both sides. And you can do these, you know, however many steps it takes. Just make sure you don't make any errors. So I've moved the x over. I'll actually just do it out. I'll just keep it a little bit more formal at the start. Is equal to plus 10. Now I'll move over the 8, just so that I know some people hate this stuff, so I want to make it. Now I'm going to add 8 to both sides. I get 7x minus x is equal to 10 plus 8, which is 18. 7x minus 1x is 6x. I'm just double checking now to make sure I haven't made any mistakes with minuses. And finally then we divide both sides by 6, and we get x is equal to 3. So, first problem for you guys to try, just pause the video, have a go at that. I'll move on. Again, you will be examined on these questions, so make sure you attempt them. Now we take a look at quite a complex looking linear function. Again, we suspect it's linear because the highest power is 1 in everything. And what we have to do here, guys, is called cross multiplication. There's a few different ways of going about it, but cross multiplying is probably the best way. So I multiply those two bits together, put brackets around both bits. So 9 by x plus 1 and then we multiply the other diagonal, is equal to 5x minus 6 multiplied by 4. Be careful here, guys. The main mistakes people make are just not paying attention. So multiply through 9x plus 9. And here, guys, we have 20x minus 24. I'm going to bring all the x's to the right hand side because that's where things will be positive. So I'm going to subtract 9x from both sides. So 9 is equal to 20x minus 9x minus 24. Now, guys, I'll add 24 to both sides to move this guy over to the right. So we'll get 9 plus 24 is equal to 11x. This gives me 33 is 11x. And finally, we end up then with x, divide both sides by 11, and we get x is equal to 3. Just double checking that I haven't made a mistake. I hope not. Now there's a problem for you guys to try, very similar. And again, we'll check out this in the next lectures. So I leave that up, guys. So that brings us to the end of this lecture, I'm pretty sure, yep. So thanks again for listening, guys. I leave that up so you can practice away. Thanks for listening. This is a bit of a shorter one. So the lectures, guys, I'll try and keep them the same length, but it's just, that's just the nature of the way the module is going to roll out. Some lectures will be a bit longer, like lecture 1, and then lecture 2 then is a little bit shorter. So I'll try and keep over the week, I'll try and keep the amount of time you have to listen to videos about the same, but some lectures will be longer, some lectures are shorter. It's just the nature of the course. So thanks again for listening, guys. We'll finish it up there, and we shall see you again for lecture 3.